Hi, so let's look at the universe as in a big picture. So in summary, we're going to cover this topic in 30 minutes lecture. Well, so what is universe? The universe is everything. It's all the stars, planets and galaxies as well as the other forms of matter. The universe also includes visible lights and other forms of energy as well. So universe is the huge thing that's surrounding us, right? So it's not only the planets, it's beyond that. So astronomers think the universe contains hundreds of billions or even trillions of galaxies, that basically the observable universe. So most distant galaxies observed to date are over 13 billion light years from Earth. There are probably galaxies even further away whose light has not yet reached us. So when we were learning about light, we know that light takes some time to travel, right? So that light, that older stars' light maybe have not reached to us yet. So universe is organized into galaxies, superclusters, and huge string-like network of galaxies in space. So most of the universe is empty of visible matter. So this is a cool picture of network of galaxies. So since the early 80s, we have began to learn how the universe is organized. It's organized into galaxies and grouping of galaxies called superclusters. The networking of galaxies called filaments stream across vast distance of space. So if you attended the planetarium show, we have had a chance to look at it in three-dimensionally. So how old is this universe? As we know, the universe is about 13.7 billion years old. The age was determined the age of the oldest star and the distance between galaxies. So the galaxies are moving around and it's basically expanding. So universe must be older than the oldest star. Stars did not begin until about 400,000 years after the Big Bang. So oldest star found so far are about 13 billion years old. So all faraway galaxies appear to be moving away from one another. So scientists know how fast the galaxies are separating and how long it has been since the Big Bang can be calculated. So this picture is a very famous picture that you can find out even in online or in textbooks, right? So what does this picture represent? So we think that the Big Bang happened somewhere here. So a ray of light pattern 380,000 years later here. Then there was a dark ages. Then the first star is born in 400 million years later, the Big Bang. And all these galaxies are in the space. So this represents the Big Bang expansion for 13.7 billion years. So all these galaxies are expanding, as I mentioned earlier. So that's why the shape is look like a bell, right? So this represents the expansion of universe and also the time or the distance to the galaxies from the Big Bang. So is universe changing? So we can agree on that, but do we have data? So this is a really nice and very interesting picture. So Stephanie's quintet provides a rare opportunity for astronomers to observe a group of galaxies in a crucial stage of its evolution. So 5 galaxies in a group called Stephanie's quintet are colliding and changing as shown in this picture. So this picture was made by combining photographs from several kinds of telescopes. So here there are 5 galaxies. So let's count. So here's a 1 over there and 2, 3, 1 over here it's 4 and this is the 5th one. So there are 5 galaxies over here and it's represent the different ages of these galaxies. So these galaxies were discovered about 130 years ago and located about 280 million light years from Earth, a view and optical light from the Canada, France, Hawaii telescopes on Mauna Kea. So this clearly shows 4 individual galaxies, 1/5 hard to see galaxies is plunging its way through the system at almost 2 million miles per hour. So this extreme motion generates shock waves that heats the gas between the galaxies. This in turn causes the gas to glow strongly in X-rays, and we can observe those X-rays using our Chandra X-ray observatory. So these pictures are really cool and they are real, but we're using X-ray technique to develop these pictures. So for a very long time, astronomers thought the universe never changed. In 1924, American astronomer Edwin Hubble was the first to prove that there are other galaxies beside the Milky Way in the universe. You know, Milky Way is the galaxy that we live. So he also showed that the universe is expanding. He studied a faint patch of light in the sky and showed that the light was actually a large group of stars that was 2 million light years away. Gravity causes galaxies within the same cluster to stay closer together and even at times to collide. So Hubble found that those galaxies that were far from each other were growing even further apart. So further the two galaxies are from each other, the faster the distance between them grows. So in summary, yes, the entire universe is expanding. We can use a simple model to demonstrate the expansion of universe. So think about a balloon that's with embedded coins in there. So when you blow gas into the balloon, the coins are getting separated from each other, right? This is on the surface of the balloon. So this is not on the center of expansion, right? So here, this is the center coin, and all these galaxies are moving away from the center coin, but the distance, the ratio that is moved away from the center galaxy will stay the same. So the expansion constant is kind of a constant value. It doesn't matter which galaxy we are talking about. So here's another picture of galaxies that are moving through the space. So due to the expansion of the universe. So as space expands, the universe carries the galaxies along with it. So here's the 4 galaxies, but let's say over the time universe is expanded, so the galaxies are separating from each other. And here it shows the most expansion of the universe, and the galaxies are apart from each other. So most galaxies continue to move away from each other. So in the Hubble's law, he plotted the velocity of recession of these galaxies and the distance in millions of parsecs. And then here's another graph of recession velocity in kilometers per second and the distance. Okay, so this plot shows the relationship between distance and recession velocity. So as you see, it does have a linear relationship. So the recessional velocity is equal to a constant times the distance to the galaxy. So here the slope of this graph represents the Hubble constant. That is the constant that's in this equation. We note it as H naught. That's the Hubble's constant, and it is a constant value, right? So it's not changing. So the values of Hubble constant is currently uncertain, but with an estimation ranging from 50 to 80 kilometers per second for mega parsecs. So this H naught value can be somewhere in between 50 to 80, but we are a little bit uncertain yet. All right, so what was the Big Bang? So maybe you have heard it a lot, and maybe you have watched cool videos about Big Bang. So most astronomers think that the universe began expanding in a sudden, violent event called the Big Bang. According this theory, the Big Bang marks the birth of the universe. Astronomers think the Big Bang occurred about 13.7 billion years ago, as I mentioned earlier. So the universe was very hot right after the Big Bang. As space expanded, the universe began to cool off. Eventually, the universe grew cool enough for matter to form into stars and galaxies. Evidence to support this Big Bang theory are So here, this is a map of the universe created by a space probe, shows slight differences in temperature of the cosmic microwave background radiation. So these are the microwave background radiations. So as you see, there are color differences, right? That's represent the temperature differences in the space. So blue represent the coolest temperatures, red shows the warmest. So these CMBs, the cosmic microwave background pictures, is the most ancient form of energy ever found. So how big is the universe? So scientists have hypothesized that the universe contains more matter than can be directly observed with telescopes or other instruments known as dark matter. So as you see in this chart, 21% dark matter over here, and the normal matter is 4%. 75% dark energy is there. So the composition is changing from 4% normal matter. So this is what we can visible using our naked eye, right? So, or using our instruments as well. So although dark matter cannot be seen with telescopes or other instruments, scientists can tell it's there by observing the effects of its gravity on the other objects in space. So for an example, galaxies have much more gravity than can be explained by the stars and other matters that we can see. So there should be something in there, like invisibly, making those gravitational forces to accompany that missing piece of the puzzle. So gravity depends on the mass, amount of matter. So therefore, these galaxies must have some form of invisible matter that increases their mass. Is the universe expanding faster than it used to? The universe has been expanding since the Big Bang. Scientists once believed that the gravity was slowing down the expansion of the universe. So in 1998, astronomers announced that supernova in distant galaxies appeared dimmer than they had expected. This suggests that the expansion is actually speeding up. This speeding up involves a mysterious type of energy called dark energy. So this energy appears to work against the pull of gravity, causing the universe to expand faster and faster. So here, if you look at this picture closely, you see this fuzzy ring can you see a dark fuzzy ring? So that's indicate the presence of dark matter in an image taken by the Hubble Space Telescope. So the ring appears because light from galaxies at the center of the image is being bent by dark matter in front of them. So here the center of this galaxy, but here these are dark regions over here. Even though we can't see anything in there, but the lights get bended. So we can come to a conclusion that there's something over there filling this space. So that's called the dark matter. So when the slices across the universe and back into time are combined, they make three-dimensional map of dark matter in the universe. So as you see here, these are the slice pictures of the universe in the first one is 3.5 billion years ago. The second one is 5 billion years ago, and this is 6.5 billion years ago. So as you see here, it's all crunched together, but later it's get expanded, right? So the three axes of the box correspond to sky position. So here, the sky position, and that's basically the right ascension and declination, and distance from the Earth increasing from left to right. Okay, so 3.5 billion, 5 billion, and 6.5 billion years ago. So it's going away from the Earth. So the clumping of the dark matter becomes more pronounced, moving right to the left across the volume map. So from the early universe to the more recent universe. All right, so I'll see you in the next video, and let's categorize galaxies into different types.